Today, in our video, we will see the design of conformed steel columns. So I have explained in the previous video in a very clear manner the difference between the hot rolled steel sections and the cold formed steel sections. We also went through the different terminologies like the effective width, flat width, stiffened, unstiffened elements, all those things. So after going through the basic terminologies, please watch this video for a better understanding of the design of steel columns, column steel columns. So to design the column steel column, we do have a different Indian standard code. We're not designing with the IS 800. So this is IS 801, which is therefore designing the column steel. So I will scroll the PDF. The title of the IS code is Code of Practice for use of cold formed light gauge structural steel members in general building construction. Right, and when you scroll again the terms, again the title, and the first introduction, then the scope is for the cold form steel members, and the various definitions we already seen in the last video: stiffened compression elements, unstiffened compression elements, multiple stiffened elements. We already went through the flat width ratio, effective design width, thickness, and the terminologies like torsional flexural buckling. Stress all things we went through, and the design procedure, the properties of sections. So here I'll tell that we have the steel table which have the details regarding various sections of hot rolled steel. Similar to that, for cold form steel, we have IS 811, which is the steel table for cold form steel. Okay, when I just scroll through, you can see different cold formed steel sections. Their properties are given in this code IS 811. So back to IS 801. So that's about the properties of section. Then, yeah. So we have discussed the important term called effective width in the last video, which is the width which is actually participating in taking the load, or the width we are considering to be fully effective in taking the stress. So the effective width is different for load determination as well as for the deflection calculations. So, and similarly, the effective width calculations are different for the open sections as well as for the closed sections. So you can see for load determination, the flanges are fully effective. That is, entire width B will be equal to the effective width W up to this limit. So if the W by T, where W is the width of the flange by thickness, is less than this value, then the flanges are effective. Okay, so it is fully effective. So this is a limiting high upper value, and this is the calculation for B by T. And as I told, the for the closed section, there is flanges of closed circular, sorry, square or rectangular tubes. We have a different W by T limit and the different uh, B by T calculations. You can see here the initial part is same, but the inside the bracket the constant is changed. So there are different limits for open section and as well as closed square and rectangular tubes. That's the main takeaway from this portion. And similarly, for finding the deflection, there are different effective width similar to the previous one, that is open section has got different W by T limit, which is actually higher than the load limit 1435 1850. And similarly the B by T is also higher 2710 here. Previously it was 2120, and the inner values will change. It means inside the bracket value will change. And yeah, same for the closed, square, and rectangular sections. So these are important for finding the effective bits which are required for the design as well as for the analysis. And for the multiple stiffened elements, it is having some more modification to the equation, and this is not in the syllabus. And thereafter, there are portions on stiffness for compression elements, the intermediate stiffness, the maximum allowable overall flat width ratio. So these are the maximum allowed values for different sections. That is for angle section, for unstiffened compression element. This we can't go beyond this one. If the value is higher, it will be very slender and it will buckle very fast. Then initially wide flanges. After that, the maximum allowable web depth is also restricted by for unstiffened and the stiffened and for different type of loading. And thereafter in the code, so from here, section 6 of IS 801, the design for compression member starts. And one more thing to tell, that is this code is actually IS 801 1975 code, and it is reaffirmed. That is, all the contents were again sanctioned at the year 2010. So the basic design stress is given by F is equal to zero point 0.6 into Fy. So if the yield stress is some x into zero point 0.6 times will be the design basic stress. Then the some inputs, general inputs. Thereafter, if there are some wind earthquake loads, we have to take the stresses 33 percentage higher than those specified for the deadland live load stresses. Is the extra loading causes or it could be accounted through an increase in stress in the material, so that we have to design accordingly. And also this 6.2 gives on the compression on unstiffened elements, different criteria for W by T not greater than, so this FC is actually the allowable descent stress. And again for compression FC, uh, for flat and stiffened elements there are some values for different W by T ratio, and this is the design for the laterally unbraced beam, which is not in the syllabus. You're just designing for the braced beams. And the 6.4 is on the design for beams, that is allowable stresses in the web of beams. And the bending stress in webs, and the web crippling in beams. You know well what is called as a web crippling. So these are some advanced things, and I just want to show you that these things are there accounted in the IS code. And axially loaded compression member, again like the the section number 6 was on the design stress, and 6.6 is actually the equations for loaded compression members, axially loaded compression members. And for 6.64 and 1.1 is on shapes not subjected to torsional flexural buckling. There are some set of equations which we'll see while doing the problem to make it clear. And for there are for non-symmetric or singly symmetric section, there are some additional criteria because of the torsional buckling which will occur in the non-symmetric or singly symmetric sections. And then 6.7 is on the combined behavior for axial loading and bending stresses. Like you studied in the structural design course for the interaction equation for combined shear plus bending as well as axial force plus bending. And let's scrolling down. Yeah, so these are the main contents in the Conformed steel, and the 7.7 is on connections, which you don't want to study for the syllabus. And water connections, welder connections, the bracing requirements. Yeah. So these are the contents of the IS code 801. And similar to this, we have I mentioned that 811, which is the steel table for the conformed steel, conformed, sorry, conformed light gauge structural steel sections. We're scrolling down. The introduction part, some basic definition, some titles explanation, the corrosion protection appendix for calculating the rotation thickness at curves. So these are some inputs for finding the section properties. And the equal angle, the designation, how the equal angles are designated. It is 20 by 20 by 1.25 means 20 is the width, 20 is the height, or it's like both the widths. So this portion, this flank portion is 2020, thickness is 1.25, and all the values are given. Moment of inertia, radius of gyration, section modulus are given as in the steel table for this cold form steel members. Unequal angles having different sizes, 20 by 15. Then channel without lips, rectangular shape. Um, Channel with lips is this portion which is the extension of this flange. So this will ensure more stability for this cross section. Channel with lips, rectangular. And this is a hat section rectangular, rectangular, different p greater than h. The lipped z sections, equal flanges, so this flange value will be same. There will be as a nest we have the properties, so based on the thickness we can find the, so if the thickness is given to you, that we can find the radius and the radius thickness, all those things values are given for a 90-degree corner in as the last portion in the IS 80, sorry, 811. So I have already shared this PDF to you on the Qualcomm steel design. So that PDF we have 16.1 as introduction, then the various conformed steel shapes. These are the various shapes, and we already went through these definitions in the last video. The stiffened compression element, the unstiffened compression element, then the multiple stiffened element, the definition for flat width ratio. So again, so this width to the thickness ratio, flat width, excluding the corner. Then the effective design width. So this will be the effective design width for this channel section, and this effective width as we seen in the last code that the effective design width will be different for the load as well as for the deflection. and the different properties of sections, local buckling of plate elements. We have seen that the different properties of this corner angle. For this corner, we have seen in 811 the last table regarding this one 90-degree corner. Here we have seen this one. Yeah. After that, um, some plate buckling theory part, which is not in the syllabus. The pivot method explanation. So the buckling of plates. Yeah, this I was telling. This also in the code that the load carrying capacity is given by these equations, and for load determinations, we have b different b by t value surrounding of 2120 by root of into 1 minus 465 by w by t. For deflection, you have a different b by t equation with a limiting factor. So see this 2710 and 1813 here in IS 801 1975, and for the tubular section we seen that there is a different equation for load as well as for the diffraction determination 120 2710, and this is an important thing before we look into the problem. IS 801 1975 is still in the MKS unit system. Okay, so it is in meter kilogram second, and it is not revised to maintain SI units throughout the book. For this book, they have actually converted this MKS unit to the SI units. The formula given in the code are converted to SI units and are presented in table 16 point. So they have converted. So this left side MKS unit will be the equations which will be in the code, and in this textbook and in most of the textbooks actually they converted MKS to SI units. So wherever in the textbook the problems are done using this equation, you have to use the left side equation which is actually available in the code. So the law determination for the deflection different values, and also for different section different values. Corresponding SI values are given on the right side. And this is the important thing, that is the formula in SI units can be obtained by dividing the constants of the equation given in IS 801 1975 in MKS unit by a factor of this. It is 3.22, where uh, it is actually 2 lakh, sorry, it's 20 lakh 74,000, and 2 into 10 power 5 are the values of modulus of elasticity in MKS and SI units respectively. Also, the multiplying factor for stress conversion from MKS to SI is 0.0981. So, by multiplying these MKS unit values, it is codal values, by these constants, you can get these SI values. For example, SI equation 16.7. We'll see 16.7. 16.7, I think 16.7 or 1. We go past. The equation is this one. B by T is equal to 2736 by, so 2736598. Okay. Can be converted to this value 850 by root of into this by conversion using these values. And in this equation the mu is the Poisson's ratio is substituted here, and F max, F are the actual, F max is actual maximum stress in combustion element, based on effective design width and FS actual stress. And specifications stiffness you can skip for time being. Maximum allowable flat plate, they are the constant values which you have seen in the code also. And effective design width for short span beams. Okay, maximum allowable web depth, we have seen that in the code, 150 200. Deflection of the beams, uh, yeah, deflection maximum is actually span by 325. And basic allowable design stresses for different yield strength is given in this table, but this is actually I think it's not available in the code. You'll see when you go through the code. Check it fast. We'll see that later, or you can explore yourself that one whether this is available in the code. And allowable compressive stresses in unstiffened element. Some values are given, and allowable stresses in unstiffened compression element. We have seen that in the S code A01, and same thing. This is also converted from MKs to SI units in this textbook. This I can show you. We are almost near to that. Yeah, this one 6.2, compression of unstiffened elements. Compression of unstiffened compression elements. Yeah, same thing. Compression member. So here onwards the design for the compression member starts, and in this um, portion there is an important term called form factor. We just read through. The column strength of thin plates is defined as the load carrying capacity of the member controlled by one or a more combination of type of failure. So there can be crushing of the plate in the cross section. There can be local buckling of the thin plate elements, overall primary column buckling, and also torsional buckling. So these are the predominant modes of failures for a column. In cold-formed light gauge sections, the width thickness ratios of component elements are large enough to cause local buckling. So if the width is very high on comparison with the thickness, it is very slender. So necessitates the consideration uh, of the local buckling effects in the allowable stress computations. This is done by incorporating a factor called Q, which is a form factor, and in the allowable stress expressions, the form factor is less than 1, and by substituting QF. And there are different expressions given for finding the form factor for members composed entirely of stiffened elements. So this is entirely stiffened means it will be a closed section, and there is an equation given for members composed entirely of unstiffened elements. There is only an angle section because at least for this channel section this is stiffened. Okay, the channel both the legs are unstiffened, and the member consisting of both stiffened and unstiffened the majority of the case, and there are some other equations for finding the Q form factor. And for point symmetrical Z section there are some expressions for finding the Q. And the web of beams, the maximum shear stress allowable are given in this portion. So this will see when you are designing for the beam. Bending stresses in webs, combined bending and shear stress in the webs. So there will be interaction equation, and web crippling of the beam. So this is called web crippling. As the figure is here. So the web, this is flange and this is web, and the web will cripple upon loading. Here also the web is crippling. This is essentially buckling for the web. Beams having a single unreinforced webs. Okay, some equations are there. So those things are there. So we will go back to that equations whenever the problem demands. Okay, so we'll first see the problem of a closed section. So just to remind you again, we are going to analyze the closed section as a compression member. So please remember that I told for deflection calculation and for the load calculation, effective width are different for open and closed sections. So we have a different set of equation for this box section. Okay. So the problem, they find the column section properties, where to find the properties of this column section, and allowable load for the column section shown in figure example 16.1a. The effective length of column is 3 meter. Fy is equal to 235 Newton per mm square. Okay. So the straightly the into the values, solution linear properties. Radius of corner r is equal to 2.4 plus 0.8. So thickness of this rectangular closed section, the square is equal to square, I guess. 120, 112 plus 4 plus 4. So 120 by 120. Yeah, here 120 by 120 square closed section. And radius of corner, actually this won't be given in the problem. We have to see the IS 811, last one. Here the thickness is 1.6, 1.6 here, and the value of radius is 2.40. Okay, so this 2.4, and please note that this radius is actually from here to the center of this uh, element. So we have to add one more half the thickness to complete the total value of the radius, which is given by 2.4 plus zero point 0.8 is 1.6 by 2, 3.2 meter, 3.2 mm. Length of the corner, total length of the corner is given by 1.57 into r. That value, yeah, so the length of the corner is 1.57 into r. We can learn by heart. 1.57 into 3.2, 5.02 per mm. Cxs is equal to 0.637 r. So these values I just show you. Yeah. So these are the actually properties of this 90-degree angle section. I C 0.637 r, 1.57 r, and yeah. You have to learn these values. Then I1, I2 is 0.149 r cube, and I3, I4 is 0.75 r cube, which are the properties of this section 90 degree. Back to the problem. Yeah. So Cxs is equal to 0.637 into r will be equal to 0.637 into 3.2, 2.038. So this r is this one 3.2, and total length is equal to we are taking the perimeter of this section, and 2 into 112 plus 2 into 112 both sides plus 4 into 5.0624 length of the corner. Yeah, 468.1. So the area will be equal to total like perimeter into thickness will give you the total cross sectional area. And taking the moment of inertia, I axis about this axis, you can take uh, two webs about this central axis, then two flanges and the four corners. So the two webs, uh, two two flanges, and also the four into means these four corners will give you the moment of inertia, and the actual I axis is equal to 1.10, this value into 1.6. Yeah, so this 1.6 is actually thickness, and we have radius of gyration given by r is equal to root of ix by a, which will be 4.8 centimeter, and we know that design stress is 0.6 into 235, which we have seen uh, S6, yeah, here. So zero point 0.6 into Fy. To calculate the form factor, we need the effective width and effective area of the cross section. So for that, we are actually here that SI equation is used. So in the textbook itself, SI equation, you can note that the value is 478 by root of 478 by root of. So coming to that page, so yeah, so you can see here SI units, that is load determination, combustion elements other than tubes here, deflection other than tubes. For tubes, we have load determination 478 by root f. So this is the value. You can either use that 1540 by root f, which is available in the IS code. So we are using this equation and we are checking with this. So please note down this value 478 by root f and 658 130. So just to remember those things. So those equations are used here. W by T limiting value is 40.25, and we found that W by T, where W is actually the 112, excluding the rounded corners, by T is 1.6 is 70. So W by T value is actually exceeding the W by T limit, and the V by T is given by applying the equation. We have got 46.75. Then so B is equal to this T is going to the right hand side. B is equal to 74.8. So this means that just a minute. You can see here that for W by T up to this limit, we have full section effective. As our value is higher than the W by T limit, we are using this equation 658 and 130. Okay. Yeah. So as the section is not effective, 74.8. This means that out of this 112, only 74.8 is effective. Then the total perimeter minus this how much reduction for 37 points reduction from 112. So the effective area got reduced from actually 748 to 510. Right. Then the form factor. So please understand that the form factor equation is also different equations for different sections. Okay. Yeah. In the IS code, you can see 6.6. The 6.6.6 sorry 6.6.1.1 for the shapes not subjected to torsional flexural buckling, the set of equations. And then after that, as second, we have singly symmetric and non-symmetric shapes, those things. So back to that PDF in 16.10 compression members, determination of form factor for the members composed entirely of stiffened elements. So this is the stiffened element. We have actually the P ultimate is equal to A effective into F by. Yeah. So in the PDF, textbook PDF, we have the form factor given by Q is equal to A effective by A. It is 0.682, and then as we seen in the 801 code, the same one for the doubly symmetric box sections, we are supposed to find the CE, Q, all those things where the CC is equal to root of 2 pi square E by F by, and the Q is actually the form factor which we have just found out. So the C is equal to root of 2 pi square E by F by, we get 129.61 L by R limiting. It is actually the K in the L by R. where cases depends on support condition. Make assume it is simply supported or both an hinge. So k is equal to 1. L by R is equal to CC by root Q, which will give you 157. So actual L by R is so we have to see the support condition. The find the column allowable effective length is already given as 3 meter. Okay, so already it is given as 3 meter. Then 3 converted to because R is in R is in centimeter, and we just converted the meter into centimeters to get the actual L by R is equal to 62.5, which is less than 157. So we have a set of equation. If the KL by R is less than CC by Q, we have this equation. If KL by R is equal to or greater than CC by Q, we have expression this. So we are using L by R is less than 157. So we are using this uh, first equation 12 by 23 into Q into F by into this much values are there. So it's the direct substitution where you can see the CC is a constant, not a constant, it's a value to find out based on the inputs. P is the total load, A is the full unreduced cross-sectional area, FA1 is allowable compression stress, modulus of velocity, effective length factor K. For hinge, K is equal to 1. L is the unbraced length of the member. So K into L will be the effective length. R is the radius of gyration. Fy is the yield point of steel. So all those values are given in the problem. That means the effective Fy is given, effective length, everything is given. So it's a direct substitution, and we can find the FA1, which is the required value. FA1. Okay, so FA1 is equal to 76.99. Then directly, this is the reduced stress because even the material is having the capacity as yield stress as 235. The as it is conformed steel, it is able to take only 76.99. So 76.99 into the effective area. There is reduced area, sorry, it is actually total area. As we are reducing the stress into total area will give you the capacity of the column. So that's about the column design.